Okay, let's get started today. First of all, very important announcement. Our first midterm is a week from today. Okay, so it's Thursday, February 12th. It's going to cover all material through today, so up through hash tables. It will not cover the material on pointers that we'll be going over on Tuesday. If I have not taught this course since it went over to C++, so I do not have an exam of my own that I can show you that is going to be of any value. So the best I could do is to give you an example. Whoops, should have been there. I will make sure that it's posted. An example exam from Dr. Plank. And that will, I thought it was already up, but I will get it up. The format of the exam is going to be different than it was in 102. It's going to be primarily problem solving. So instead of multiple choice, there may be some multiple choice, but there won't be much. Instead, you'll be expected to write some programs. You'll have to do it on paper. We don't have a code assessor for this. You may have things like I could ask you to add some hexadecimal numbers or show me what a value of a base 10 numbers in hexadecimal or octals, so small problems like that make you work something. It might be a small thing like I give you a couple of command line arguments and tell me to write a short program fragment to convert them to integers, add them up, and print their value. So you need to be prepared to write code. You need to be prepared to do some simple problem solving on the exam. You will be allowed to have a one-page cheat sheet front and back for the exam. Okay, and the exam will be an hour and 15 minutes. So, questions about that, about the material, or yes?
You mentioned converting some numbers in different bases. That's not with C++, that's by hand, right?
Yes, that's by hand. You have to do it by hand. Mm-hmm. Yes, Doug.
We actually will be like writing code by hand.
Yes, you will be writing code by hand. So we understand that in the heat of the moment you may not get the syntax exactly right. If you just completely butcher it and have, for example, no idea how to write a for loop or a for statement, you will lose points. But if you forget a semicolon or there's, tiny syntactic errors where we know what you were doing, but you just missed something small, we're not going to be, or if I tell you to write a class declaration, you forget the semicolon at the end of it, we're not going to be busting your chops. But you can't also just write pseudocode and expect us to give you credit for it. This is a course about C++, and we expect you to know how to write C++ code.
Are you looking more for like correct, like that it would actually work if compiled, or like
yes, it's both. So that's what I mean by, so our primary thing is correct logic, that it would work if run. But that's why I said you can't just write pseudocode. It has to be something that is recognizably C++. So it's going to be both. The logic needs to solve the problem, but the syntax you write has to be pretty much close to perfect. You're allowed to have small bobbles, but you've done enough C++ programming at this point that you should be able, especially with a one-page cheat sheet, to be able to get the constructs right. Yes, Jeremy?
Besides the old exam from Dr. Plank's class, will you post a review guide or anything?
My notes, the notes that we've had so far are the topics. You can pretty much go through the lecture notes and they tell you what the topics are. It's Unix VI files, it's reading, go through the notes because that is the set of topics that we will be going over. Yes?
Could there be questions about the Unix and VI communities?
No, it's not going to be at that. If I did, okay, let me take that back. Maybe, but that would be, if I did, I would do it in a multiple choice. Okay? I don't consider that as crucial. So if I did, it might be, for example, if I want to create a copy of a file in Unix, which command should I use? VI, CP, MV, MKDIR, and your answer would be CP. Okay, so I wouldn't expect you to pull that stuff out of memory. Okay. Other questions? Okay. So, also, let's see. Okay, so just again, so that you're absolutely clear, you have a one-page cheat sheet, front and back. You can cram as much information onto that thing as your heart desires, as long as you can read it. And the other thing is, beyond that, is closed note, closed book, no electronic devices. So for example, you should be able to convert from base 10 into octal or into binary or into hexadecimal on your own, using your own wits, not requiring the help of a calculator to do so. Okay, so today we're going to be finishing up hashing. As I said, this is the last topic that will be included on the exam. And just as a quick review, what hashing is intended to do is to efficiently map keys into a table. And so like Dr. Planck's notes say, you have a hash table, which is typically a vector. And I added a few updates to his notes yesterday. The hash table size should typically be prime. Should be a prime number. And it just so happens that you get much better behavior if the hash table size is a prime number. So even though his notes illustrate a hash table with a table of size 10 elements, your size should be a prime number. Then there is a hash function which takes the key and it converts it to a entry in your hash table. So typically the hash function is something that it's some function that returns some value and then you mod it with the table size. Okay, when you have that key, then it gives you an index into the table. Okay, that's what you do with that hash code. So we call that thing a hash code. Okay, so we'll call what you get out, we'll call this thing a hash code. Okay, you use that as an index into your hash table. So if you're trying to find the key, that's where you start your search for the key. If you're trying to insert the key, that's where you would like to place the key. And finally, there is collision resolution strategies because sometimes you will have two keys that end up wanting to go into the same location in the table. And then you have to have a way to resolve the contention for that spot, because ultimately both keys need to end up in the table. The other thing that we didn't perhaps mention as strongly on Tuesday, but probably you got some hint of in the lab, is that typically you're not just storing a key, you're actually storing what we call a key value pair. Okay, so typically what you're storing is a key value pair, so that you want to look up the value associated with the key. The example I gave on Tuesday was word frequency count. So there the key was the word, and the value was its frequency count. Okay? In the lab, the key is a bit confusing, but the key is the hashed value of a file, of the contents of a file, and the value is the file name. So you typically have both a key and a value, and there's two ways that you can store these key value pairs. Okay, so two ways. The first way is with two vectors, which is what you're doing in Lab 4. So you could use two vectors. Okay, one for the key and one for the value. Can someone think of a second way to do it?
Like a vector of classes.
Very good. Vector of classes. So use a class to pair the key and the value. Okay, so use a class to store both the key and the value, which is what you'll do in Lab 5. And then you'll have a vector of classes. Yes?
Can you use the multi-map?
Okay, so you could use the STL library, but if that's what you're referring to. But right now, so the answer is later, yes. Right now, we're trying to get you to understand how those multi-maps are implemented. So it's kind of like these are the two strategies that a multi-map might use to store it. Okay, so a multi-map, I guess, is higher level. Okay, so those are the two ways that you're going to potentially store the key value pairs. In fact, approach 2 is more common, even though in Lab 4 you're using approach 1. Okay, so as I said, the only big thing about, there's a couple things when you select the hash table. Okay, so first of all, size should be prime. And the second thing is what the size should be. And it depends on what type of scheme you're using. If you're using separate chaining, then it should be roughly the size, the size should be equal to the expected number of keys. Okay, if you remember from last time, that gives you an average load of 1. That is the number of entries per bucket on average is 1. Whereas if you're using open addressing, the other 4 techniques, so of which one of them is linear probing, then the size should be roughly 2 times the expected number of keys, because as the table fills up, the performance degrades. Okay, in fact, I added a little performance comparison that we'll look at the very end. But in general, you need to start with a table roughly twice as big for open addressing. But the trade-off is that's all the storage you would need for open addressing, whereas with separate chaining, each bucket or each entry has a vector associated with it. So those vectors constitute additional memory, and those vectors will grow as you add keys to your table. So in general, separate chaining requires more memory. Okay, so questions about the hash table. Those are the two big things. Selecting the size and making it be a prime number. Okay, then the next thing is choosing a hash function. And remember, we said that in order to avoid worst case performance, you want the hash function to uniformly distribute keys over the hash table. So basically, any bucket or any entry should have an equal probability of receiving a key. And there has been, thousands of hours of research into this, many papers published on different hash keys. So at the beginning of the Lab 4 write-up, Dr. Planck talks about two very sophisticated ones called SHA and MD5. Those are very sophisticated ones. He doesn't even give you the algorithms for them. Then he also, in the lab, gives you two other ones, last 7 and XOR. And in the notes, you get 3 more. And the number beyond that is even much greater. Okay, so normally you're going to use a hash table from a library and someone else will have provided that hash function for you. But you should know something about how hash functions get computed because they all have some very common characteristics. Okay, actually, before I say that, another thing I just want to mention is that most of the research is on how to hash strings into numbers. If your key is a number, typically the hash function is pretty easy. Typically, if the key is a number, okay, so if the key is a number, you typically just take the number and mod it with the table size. Okay, so if it's an integer or if it's a floating point number, you'd convert it to an integer, like zip codes. Okay, if I was trying to map zip codes to cities, okay, oftentimes if you're entering your address on a web page and they ask for a zip code and it automatically fills in the city and the state, they're using a hash table. Well, zip codes are very well distributed between 0 and 99,999. So a reasonable hash function for a zip code is to simply mod it by the table size. And in general, we expect numbers to be well or uniformly distributed. So that real research is on how you hash a string into something. So what we're trying to do is find out a good hash function f that will return a number that is uniformly distributed between 0 and some very large number. It'll look like it's a random number. Okay, so in his notes, Dr. Planck has 3 such functions. He starts out with one that is very bad. Okay, it's very simple, but it's very bad. Okay, and that is he simply adds up the ASCII character values. So for example, if you have a string like, say, A, the ASCII value for a small a is 97, and the ASCII value for a large A is 65, so you just add them together and you get 162. Okay, so it's a very simple algorithm. You see it right there. You declare your hash value or your hash code H to be unsigned. And the reason, does someone know why we declare it to be an unsigned int? You want positive numbers, exactly. You don't want a negative number, so you declare it unsigned. And what happens when you calculate hash codes is you frequently get overflow, where the number becomes so big it overflows the 32 bits. And that, if you're not careful, could cause the number to appear negative because that last bit could end up signaling that it's negative. But by declaring it as unsigned, it doesn't matter if the overflow occurs. If the numbers become so big that it overflows the 32 bits, we don't care. Remember, we're trying to get a random number, so if we lose some bits, we're okay with that. If we declare it unsigned, we're guaranteed the number always stays positive. So here, it's a very simple thing. We just iterate through the string. We add the ASCII hash values we return. Can someone suggest why this is an incredibly bad hash function? Why we may get very poorly distributed hash numbers? Okay, because it seems to me on the surface that it's fairly reasonable that your strings, you know, they could be somewhat random. Yes.
Since the ASCII character values are over a limited range, adding them up, you're going to have a lot of the same letters. You're going to get close to the same value for each string.
Okay, so one thing that happens, good, is even if they're random, they're a lot in the same range. So you're going to, it's very easy for something that's ABB and BAAB are going to hash to the same code. In fact, any combination of those letters are going to result in the same hash code. That's not very good. Okay, that's just things that seem very different will all hash into the same entry. So just the fact that the letters, there's only 26 or 52 unique letters, and you're going to tend, remember this notion of reversion to the mean? There's going to be this tendency to revert to a mean of an average of whatever 65 is plus 26 is 91. You're probably going to end up with your average value being around 78 or 79. So you're going to get this reversion. So that's one bad thing. It's not nearly as random as it looks. Okay, there's a second issue. Even if it was very random, Mark.
It's not uniformly distributed over the size of each or the size bin.
It's not very good. It's not uniformly distributed over the range of h, which is a 32-bit number. Okay? Most of these, because the values don't get much higher than about 120, and typically your words aren't that big, you're going to end up with a lot of relatively small numbers. Your hash codes aren't going to be anywhere close to 32 bits long. And Dr. Planck gives an example where he has a hash table that's 100,000 entries. Okay? Well, you can't really expect to get very many keys that hash to a value that's greater than, say, 1,500 or 2,000. So you're only occupying, in that case, maybe 2% and probably much less of your potential hash table size. So it's definitely not uniformly distributing these hash codes over the entire size of the table. So there's a lot of problems with this particular hash function, and we don't recommend that you use it. So instead, the general strategy is that you actually treat the numbers or the letters in the string as though they were numbers of some kind. Okay? So one thing, if you knew they were all lowercase, to make it Brad, you might say that they're base 26, with A being 1 and B being 2 and C being 3. So you might treat them as base 26 numbers. That will definitely cause the numbers to get big much faster. Okay? The hash tape, the next one we consider is kind of a variation on that. I'm not going to even go into how they come up with these because it really does take a lot of mucking around and experimentation. Dr. Planck points you to the web page for this one. But their calculation for the next one comes from the University of York, and he abbreviates it DJB. And that's the function. So what you're doing is you're building up your hash codes. So you start with your initial value for the hash being 5381. And then as you look at each successive letter, you multiply the previous hash code by 33, so you really blow it up. And then, while they said you use something called bitwise exclusive OR, in fact, the actual algorithm that they published used an actual plus. And you will see that with what they're doing, they are basically moving, if you think of it in terms of bits, they're shifting the initial thing over by 5 bits. Okay, that's 2 to the 32nd power. And then they're adding in the ASCII value of the character. This blows up the value. Multiplying by 33 blows it up very quickly. Okay? Because you're multiplying by essentially 2 to the 5th plus 1. Okay? With 6 letters, okay, 2 to the 5th times 2 to the 5th 6 times is 2 to the 30th, so already you've pretty much uniformly covered the entire 32-bit space of an integer with just a 6-character word. And even if you don't get up to 6 characters, with, say, just 3 characters, you're already up to 2 to 15, which is pretty big, especially because you start it with 5,381 already. So this one does a nice job of blowing things up, and his experiments show that, in fact, it's very close to generating a random number, what we would think of as a random number. Now, if you haven't seen bit manipulation before, I had a quick tutorial on it that I added to the web page. It says see the bit notes. So bit shifting is something very common to hash functions. Remember I said there's a couple things that are very common to all hash functions. Bit shifting is one, because we want to do very fast multiplication. In order to calculate these keys, we want to do it as efficiently as possible. This is one case where writing hard-to-read code is accepted. Probably the only time in this course you'll hear me say it's okay to write hard-to-read code, because efficiency is at the utmost premium here. So instead of multiplying by 33, which would be a lot clearer, we do a shift by 5 bits. Okay? Specifically, the less than says to shift an integer to the left by that many bits. So here I have an example 8-bit quantity. When I shift it 3 bits to the left, you'll see that these 5 bits are shifted 3 bits to the left, and then 3 zeros come in on the right. Okay, when we bring in 3 zeros, that's equivalent to multiplying by 2 to the 3rd power, or multiplying by 8. Similarly, when we shift by 5, we shift in 5 zeros. That's comparable to multiplying by 2 to the 5th, or 2 to the 32nd. So you might have said, well, wait a minute, it was very convenient that we had 3 leading zeros here. What if there are some numbers in those last 3 bits? What happens when we shift the integer? We say they go into the bit bucket, a fanciful term for thinking kind of like there's a little bucket here, and as the bits are shifted, they spill into the bucket and they're lost. So what happens is those 3 bits are lost. What you actually see after shifting by 3 is these 3 bits show up over here. Okay, I may go back and color them to make it clear like Dr. Planck did. So those 5 bits end up over there. We lose these 3 bits. They disappear. And in this case, it's really not like multiplying. It's like multiplying by 8, but we got overflow. That's what I meant before by we can overflow when we do these operations. And if we weren't careful and a 1 ended up here, it would think it was negative. Because 1 is often the last bit being 1 indicates often a negative number. That's why we declare it unsigned, because it keeps it as a positive number. Okay, so it really is like multiplying by 8, but since we get overflow, the number you get may not resemble the number you'd get by multiplying by 8. You can do the same thing by right shifting. In that case, you throw away the lower 3 bits. So in this case, we throw away 110, and these 5 bits get shifted down, and it's like dividing by 2 to the 3rd power. So it's like doing integer division. This is more efficient than just doing multiplication. Okay, the compiler is not smart enough when you multiply by 33 to figure out that it could shift the bits by 5 and then add 1h. So bit manipulation is incredibly efficient for doing multiplication by 2 to the n or division by 2 to the n. And so you see a lot of this in hash functions. The other thing you see a lot of in hash functions is bitwise logic operators. Okay? So if you took 160, you've seen them. There's bitwise OR, bitwise AND, and bitwise exclusive OR. And here's the truth tables or logic tables for those 3 operations. Okay, so OR and AND are just like the logic operators you saw in 102. XOR is a little bit like addition. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. 1 plus 1 is 0 if you're doing it in base 2, okay, with a carry of 1. So exclusive OR looks a little bit like you're doing addition on those bits. So that's how I always remember the truth table for bitwise exclusive OR. Okay, so here are some examples. If I have 2 4-bit quantities, okay, I know in the real world you have 32-bit quantities, but I didn't want to show you the full 32 bits. So if I did a bitwise OR on these 2, okay, I showed you down here the easier way to think about it. Okay, doing bitwise OR on these 2 quantities, 0 or 0 is 0. In the second field, 1 or 1 is 1. And similarly here, 1 or 0 is 1. So it's doing a bitwise OR on each of the fields. Okay, and you can do the same thing for AND and exclusive OR. So in a real program, you see these, when you see a single pipe character, it's bitwise OR. When you see a single ampersand, it's bitwise AND. And when you see the caret, it's bitwise exclusive OR. Okay? Turns out that they're used for more than just fast multiplication or for computation of hash functions. The bit operations are also often used for the clearing or setting of flags. So remember in CN you have the EOF flag, you have the fail flag, you have the clear operation. Well, the way that C++ often implements these conditions is as bits. It keeps a single integer and it keeps track of, it allocates bits to different flags. Like it might say the first bit indicates EOF, the second bit indicates failure, ... So when you clear it, when you execute .clear, a very efficient way to clear it, you could say equals 0. But if you just needed to clear a couple of the bits, then you could AND those bits with 0, 0, and it would automatically make those bits 0. It would clear them. Similarly, if I was trying to set one of them to fail, so right now I might have this is EOF, and this is fail, I could OR it with 0, 0, 0, 0, 1, 0, and that has the effect of setting this particular bit to 1. So the flags that are often set in your streams are using bitwise manipulation. Okay, so you need to get used to them. I remember a student in 302 once told me that he thought my going over bit manipulations was pretty much a waste of time until 2 weeks later the Microsoft recruiter asked him to go through them. And then he said he was very thankful that I'd gone over them. So in fact, these come up a great deal in the real world, not just in the context of hash functions. And if you have interviews with the interesting companies like Google, Microsoft, Facebook, those companies need to write efficient software. They often care about whether you know stuff like this. Okay? Again, something I could easily ask you on the test next Thursday. So questions about that before I go on? Yes?
Those like .uf flags, where they stored in memory when you try to change them?
So you can't change them directly. You change them through .clear. So each stream object is a instance of a class. So they actually have classes too, like say iStream for CN is, and one of the fields in there, protected fields that you can't get at, might be a flag, might be unsigned, say int flags. And then it would have public clear, which is the method that you call, and clear then operates on that protected data. Okay, so in fact, when you operate on CN, CN is actually just a instance of an iStream object. Okay, so the memory for flags is actually in that object and is protected, so you can't. Obviously, it'd be pretty bad if you could get in there and monkey with them. Okay. Other questions? Okay. Also, hopefully that shows you this is a great example of why you protect your data, because you don't want people going in there and monkeying with stuff. Yes, Doug?
Are private and protected the same thing in a class?
For the time being they are, but in 365 you get to something called inheritance, and then you find out there's a difference between the two. Okay? I hate private with a passion. Okay? It kills inheritance, it turns out. So it's a huge mistake to use private ever. Okay, so if you are thinking, should I use private or protected, always use protected. Okay, they seem to operate the same way for the time being, but just get in the habit of using protected. Okay, other questions? Okay, so then moving back, so when this, you see this, what should have been, so this right here, when we calculate it, this function, this right here calculates 33 times h. The h left shifted 5 gives you 32 times h, so this is really 32 times h plus h. And then this, according to the thing, should have been an exclusive, bitwise exclusive OR, but the way they actually implemented it was with an actual plus operation. So there is a discrepancy between how the author described the algorithm and how they implemented it, which is bad, but is the way it is. But Dr. Planck went with the way it was actually implemented. Okay, the final one is kind of the nastiest one. It was something called ACM hash. Oh, okay, by the way, so then he went up with it, and you can see that as before, A was just with the previous hash, capital A was 65, lowercase a was 97, and uppercase A, lowercase a was 162. Same same two things, you get much bigger values. Okay, so it's getting a much bigger space over which it's spreading your keys. Okay, then the last thing is something called ACM hash. And it's kind of complicated to look at, but basically what's happening with ACM hash is that they're dividing, remember we want to return an unsigned int, h. So that's 32 bits. What the author did was divide that 32-bit hash code into 4 8-bit blocks. And the way you can divide it into 4 8-bit blocks is with a char. Okay, because a char takes 8 bits. And you can force a char to behave like an int. Okay, so they divide it into 4 8-bit chunks. They initialize each of the 8-bit chunks to 0, which, for convenience sakes, we use hexadecimal to represent it. So each of them can be represented using 2 hex digits. So initially they're all set to 0. Okay? And he calls them h of minus 4, h of minus 3, h of minus 2, and h of minus 1 to indicate that the first hash code that we're actually computing is h of 0. So what's going to happen is he's really kind of computing 8-bit hash codes, which he's going to jam together at the very end. So what he's doing is he's cycling through his 4-bit quantities, and he's assigning his first string, so string S0 is going into that first one, S1 is going into the second one, S2 into the third, then S4. So what he's doing is he's cycling through his 4 8-bit blocks. And he's, in effect, remember, you can think of these 4 8-bit blocks as a 32-bit word. So what he's essentially doing is at each point, he's messing around with one of the 4 8-bit parts of that word. So he's specifically adding in one of these characters at each point. And then at the end, what he's doing is he's taking whatever is in each of these 4 8-bit blocks and shoving them together to get his final hash code. Okay? So the algorithm starts by declaring, as I said, a character array that has 4 chars. Again, they are 8 bytes, and he declares it as unsigned to ensure that they don't have, that they stay positive. Okay, then he goes through, and as I said, he initializes all 4 fields to 0. Then j equals 0, that's where he's going to be iterating through j is what this is. So he's using j to go through his blocks. Okay, and at each point, he is modifying one of those 4 blocks by taking, he first of all uses the current value that is in there, the current 8-bit value, to look up a new number. So he has this so-called permutation table that permutes the numbers 256. So this is just a random shuffle of the numbers 1 to 200 and, or is it 0 to 255? Yeah, it's 0 to 255. So this is a random shuffle of the numbers 0 to 255. How the author came up with it? Probably experimented, I don't know. But he came up with this random shuffle. So each time he takes the current number that's in there and he randomly shuffles it to another number. And then he exclusive ORs that with the 8-bit quantity that is the current letter in the string. So he in effect shuffles the number that's currently in the word and then further scrambles it by exclusive ORing it. Basically, you're just trying to do everyth++everything you can to mangle it and randomize it and make it kind of unrecognizable. Okay, and he just keeps doing that. He increments J++, and every time it becomes equal to 4, he resets it to 0. Okay, so at the end of this, he's hopefully really jumbled up the contents of those 4 8-bit quantities. And when he's done, he shoves them together to form his hash code. And the way he does that, you can't just jam them together physically. Instead, he has to take each one, he basically to shove them together. So he has these 4-bit quantities. Let's say this is 3A. Let's say this is BE. Let's say this is 17 in hex. And this is 7E in hex. So what he's doing is he's starting with H is equal to 0. Then he takes the first one, which is 3A, he left shifts H by 8 bits. Okay, well, right now H is 0, so H ends up as 0. And he has 0 ORed with 3A. Well, that's just going to be 3A. So that's after, with J0, that's what he gets. With J1, he's going to have, let's get this a little more. So he starts out with H is 0. So his operation is to, if we left shift it by 8, is still 0. And then when we OR that with S of I, exclusive OR it, that's 3A, and our new H becomes 3A. Okay, now we, again, we left shift 3H by 8 bits, so that gives us 0, 0, 0, 0, 3A, 0, 0. So that cleaned up the lower 8 bits so that we can now, I'm sorry, this was not exclusive OR, this was bitwise OR. No, yeah, it was bitwise OR. Now we can bring in BE, which is this quantity. So you see that we end up with 3A BE here. Okay, we left shifted again by 8 bits, so we end up with 3A BE 0, 0. And when we OR it with 17, you see that we end up with 3A BE 17. And hopefully you see that we're going to end up with the integer that we wanted. All 4 8-bit quantities have been crammed together. And that nice left shift by 8 bits always cleared out the lower 2 hexadecimal locations, allowing us to, in effect, jam in the next word. Okay, Doug.
Does left shifting a hexadecimal by 8 only move it over 2 because it's base 16?
Yeah. Mm-hmm. So, but these are actually, I don't think I've never seen a left shift in hexadecimal. I think that left shift operator may only operate on bits. Okay, but in effect, that's what's happening. When you left shift by 8, you're in effect left shifting by 2 hexadecimal digits. Okay, but the left shift, I've always seen it expressed in number of bits.
So H is 32 bits.
That's right. H is 32 bits. It's an unsigned. It's a 32-bit quantity. So each time I left shift it by 8 bits, it's in effect moving over by 2 hexadecimal digits. Now, I know this is complicated. Many of you probably got blown away by this. You will probably need afterwards to go and look at this. Okay? It's important that you understand bitwise operations and how this is working. Okay? If you're thinking, how did he come up with the permutation table, or how did he dream this up? I don't know. Okay, that's why thousands of hours of research has gone into it. So don't worry about how he came up with this algorithm, but know how it works. Okay, know the mechanics of it. Okay, I'm not going to ask you to regurgitate it on the test, but I do expect you to know how, if I gave you an algorithm like this, I might give you code like this. Okay, and tell you what the contents of this byte hash is, and I might tell you to perform, say, 4 steps of the algorithm and show me what the result is. So while I won't expect you to be able to regurgitate it, I do expect you to be able to read code like this and be able to execute it in your heads or on a piece of paper. Okay? So, the net result, any other questions? Okay, so we come out of here and we have a 32-bit quantity that we hope is pretty random. And in fact, Dr. Planck ran some tests, and what he found was that in general, on 100,000, on a 200,000 size table with 100,000 hash values, he got roughly 78,600 unique keys out of the latter two. So the DJB produced 78,605 unique ones, and the ACM hash produced 78,610. Okay, so the question is, was that very good? So I actually was curious. I wrote a program to generate 100,000 random numbers. And of course, some of those would collide. Well, when I did that, I got 78,742, which is only about 130 to 140 more than what those two ladder hash algorithms produced. In other words, they are producing a very nicely, uniformly distributed set of numbers that look almost random. They do almost as well as I could have if I could have just randomly generated the keys. So these last two are outstanding, whereas you can see the first one stunk. It generated only 2,300 unique keys, which is terrible. Okay, and most of those were in the lower half or in the lower 2% of the hash table. Okay? Okay, so we're now down to the last part. We've got, using some computation, we managed to get our hash key. We managed to calculate f of k. That was our hash function. We now mod it with the table size. We have an index into our hash table. Now, in the best case, it's empty and we just insert it. But in the worst case, there's a collision and we have to do something with it. And last time we already talked about two collision resolution strategies. One was called separate chaining, and if you remember, all we did with the hash table with separate chaining was each entry was a vector, and as we added entries to the table, we simply appended them to the vector for that particular bucket. So if I have a hash key here, Samantha Bustle, and let's say my table size, I chose it to be 10 because that's what he did, then Samantha Bustle would hash into location 3, that's the last digit here. So I'd have Samantha Bustle, SB, right here. Then Sydney McHow would hash into 9. Okay, you can see eventually Carson Shipman is also going to hash into 3 and would simply be added at the end. So separate chaining, very simple. Okay, we also did linear probing last time. Okay, linear probing is one of 3 techniques that are globally called open addressing. Okay, open addressing, probably, I've never seen why it's called open addressing, but I would imagine it's because when you go into the hash table, you might find that your address is already taken. Therefore, you have to find another address. So it's open addressing. You are going to have to be flexible. And in general, there are 3 techniques we'll discuss, but they all have this characteristic for collision resolution. They take the initial hash key, and then if there's a collision, they calculate a second hash key, and they perform I searches where I goes from 1 to table size -1. So after a failure, they will try table size more times. So if table size was 10, they would try 9 more times to get into the table, which makes sense because if the table size is 10, there's 10 entries in there, so you'd like to try 10 times. Okay? So linear probing is the simplest technique. It simply chooses that this second hash function be I. So it's linear search. Okay, if you don't find if your location is already occupied, so already we have here Luther, Binky, Rosalita, and then D'Antonio comes in and it hashes to 1. Okay, D'Antonio hashes to 1. The first bucket's already occupied, so we do a linear search until we find the first empty bucket, which is entry 3. So linear probing is very simple. It's just a linear search until we find an empty entry. And with find, we just keep searching until we either find the key or until we come to an empty location. Okay, we'll hold off on deletion for a moment. Okay, we'll assume we just have inserts. Okay, so if we come to an empty entry and we're doing a find, we know the key is not in the table. Okay, well, linear probing has an issue which is called primary clustering, which means, so there's an issue called primary clustering with linear probing, which is that around the initial place where you want to insert a key, you can get a cluster of keys, and that can cause you to have to make a relatively large search. Like here, if I now have another key that hashes to 1, I'm going to have to go all the way to 5 in order to find an empty spot. So I have a primary cluster around 1. Okay, I actually define primary clustering later in those notes. Okay, so the very end of the notes, I actually said primary clustering, which means the keys can cluster around the initial probe location and require several searches for an insert operation to locate a free entry. That really causes the performance of linear probing to degrade. And typically, the big hit comes after the load factor becomes greater than 0.5. So with a load factor of 0.5, the expected number of probes for an insert is about 2.5, and for a successful search is about 1.5. When the load factor gets up to 75%, now the expected number of probes for an insert shoots up to 8.5. When the load factor is up to 90%, the number of probes is 50. So if you're looking at a chart or a graph that shows the load factor goes from 0 to 1 versus the number of probes for a insertion at around 0.5, it's only 2.5. By 0.75, it's gone up to 8.5, and by 0.9, it's off this particular chart. So you see something that looks, whoops, like that. So it goes through the roof as your load factor approaches 1. So linear probing, while very easy to implement, has this big issue with primary clustering that causes its performance to really tank when you get a load factor above about 50%. So there's two other strategies that we can use. One is called quadratic probing, and one is called double hashing. Okay, quadratic probing simply sets f of I key to be equal to I squared. So your hash function becomes hash of key equals whatever the original key was and that is modded with the table size plus I squared, and then that again is modded with the table size. Nice, it won't let me. Equals f of k, mod it with the table size, plus I squared, and then you take that whole thing and you mod it with the table size. Okay, so that's called quadratic probing for obvious reasons. So if we have, again, Luther, Binky, and Rosalita, then D'Antonio initially wants to go into location 1, okay? But it collides because, as you see here, actually he's doing it. Is that really right? Huh. That's different than I've seen it done before. So he didn't do the mod right here. It doesn't have any effect on the outcome. Yeah. So my way is actually the way it's done. His way, the thing is, you already have, my way is the way it's done in practice. Okay? Because you already have done this dang it. You've already done this operation. You've already got that key value. So in practice, you do it this way and then you add I squared. That is identical. It produces the identical result to what you see here. There is no difference between the two. Okay? So either way works. Okay? But my way is the way it's done in practice. Okay? So the first one, okay, you go into 1, you find there's a collision. Now you add 1 squared, okay, you mod it with 10, it goes into location 2. Okay, it's the same thing, 1 plus 1 mod 10 equals 2. Then here, 1 plus 4, which is 2 squared mod 10 equals 5. 5 is free, so D'Antonio is put into that location. Okay, now if we insert Frenchie, Frenchie would go to H2, but there's nothing, it's already occupied. So then we say that H1 is equal to 2 plus 1 squared mod 10, which is 3 mod 10, which is 3, so Frenchie goes here. Okay, and then finds do exactly the same thing. Okay, let's say that we're looking now for Baby Daisy from the Moonglow one. Let's say Baby Daisy hashes to location 2. So Baby Daisy is H0 equals 2. We can see Baby Daisy's not there. H1 equals 2 plus 1 squared mod 10, which is 3. We can see Baby Daisy isn't there. H2 is 2 plus 2 squared mod 10 equals 6. 6 is empty, so we know that Baby Daisy can't be in the hash table. Okay? So quadratic probing turns out to have very good behavior. If you do an analysis of the theoretical performance, in practice it's only about a half probe worse than the best theoretical performance that you could expect from doing the second hash function. So it's very simple and you only pay a price of about half of a probe. Now there's some issues. A big issue is that quadratic probing isn't guaranteed to look at every entry in the table. It may generate repetitions. Okay? So he shows an example here where this is his table and he generates Peach, which has this hash value. And if you go through the numbers, what do you see as an issue at some point?
Never gonna find an empty slot.
And why not? There are empty slots in that table. 2, 3, 7, and 8 are empty slots. So Doug, what's...
Because all its quadratic values are equal to them. They just happen to be equal to the ones that are filled already.
Right, so the problem is at some point right here, it starts to repeat. Instead of generating another unique entry, there's a repetition. So already we know that with this repeat, we're not going to look at one of the empty entries because we're only repeating this operation 9 more times. So as soon as a repetition comes in, we know we're not going to repeat it, or we're not going to look at least one entry. Then our next one is also a repetition, and our next one is a repetition, and our next one is a repetition, and our next one is a repetition, and we're done. We only looked at we looked at 1, 2, 3, 4, 5. We only looked at 6 entries. So quadratic probing isn't guaranteed to find an empty slot even if one exists. Now, one way that we combat this problem is we make the number prime. Okay, even numbers and non-prime numbers are more likely to result in quadratic probing not finding an empty entry. The other thing is that as long as the load factor is less than 0.5, quadratic probing is guaranteed to find an empty spot. So if load less than 0.5, then QP, quadratic probing, is guaranteed to find an empty entry. And I won't prove it. It's actually not a very hard proof, but keeping the load below 0.5 with a prime, if load is less than 0.5 and table size is prime, then we can guarantee that it will find an empty entry. Therefore, we try to keep the load factor less than 0.5 also for quadratic probing, even though above 0.5 it has better performance. Okay, then the last strategy is the most complicated. It's double hashing. It's what you're using in lab. So it takes an arbitrary second function. So the second function is an arbitrary second hash function. Can be anything else. So in lab, if you're using, for the first one, you're using last 7, then he tells you for your second one, you'll end up using XOR. Okay? So it's the same idea as quadratic probing, except that now what you have is that the hash of the key is going to equal f of k, or f of key, mod the table size, plus a second hash function, h2 of key, times I, and then this whole thing. No, that's not right. Is that right? Is that wrong? That is wrong. We mod it, just a second, because this is important for your lab. You mod that with the table size, multiply it by I, and then the whole thing is modded with the table size. So you might think, wow, modding with the table size 3 times, but you only do it once there, another time here, and then you hold the values in variables. So it's not as inefficient as it looks. Okay. So take f of key, mod it with the table size. That's your initial probe. So this is your initial probe right here. Then you calculate this value, and thereafter you multiply it by I, add it to f of key, and mod it with the table size. Yes.
So F is that last 7, and then H2 is
XOR.
Okay.
And then, but if he makes XOR the primary, then last 7 becomes H2. Mm-hmm. Okay, that's very important because he wasn't real clear in the write-up about this exact formula. This is the formula you need to use. Okay.
So do you do last 7, then you do XOR, then you add those, then multiply by I?
Yeah, no. Okay, so let me write this more clearly. So let's say you were using last 7 and then XOR. So it then would be your hash key would equal whatever was produced by last 7. Okay, you'd mod that with the table size. Okay, that gives you your initial probe, so I'll put that in parentheses. Then you would add to that XOR of the key, mod it with the table size. Okay, multiply that, just that quantity by I. Okay, and then that whole thing you mod is over table size. And you apply the mod operation. I know I can't get it all on one line is the issue. Okay? So if you look just quickly, no, I'm a couple minutes over, but I'll just give you one example and then we'll hang it up. So he uses the ACM hash value. So if this is your hash table right here, and you're going to insert Ryan, and Ryan initially, the first hash function GJB is this value, and the ACM value is that. Then you take this and you would mod it with 10, giving you 9. Okay, and you can see here he did already mod that with 10 to produce 5. Okay, and then he was multiplying, these are your i's right here. So you can see that that's indeed what he did, was he took his H2 and modded it with the table size before plugging it in. Okay, so all 3 open addressing is basically some kind of search, but each search is, or each probe is determined by a different formula. So Tuesday, I'm actually going to go over this table. That's the performance comparison, and then we're going to move into pointers. And you don't need this performance comparison for your lab.